Thank you for joining us today for our webinar on Introduction to Force Calibration. Morehouse is a manufacturing company that produces force calibration equipment and adapters that are used around the world to measure force. In 2020, last year, we celebrated 100 years in business. We're in the risk reduction business for force and torque calibration. Often we have the hard discussions with customers who may be confused, frustrated, or don't know about the importance of their measurements. But at the end of the day, we've done our job if we can help someone improve their measurements to make the world a safer place. Which brings us to our purpose. Our purpose at Morehouse is to create a safer world by helping companies improve their force and torque measurements. Today, we are presenting this webinar to help educate you on what matters most. So a little bit of background about the company. Morehouse offers deadweight primary standard calibrations that are accurate to 0.002% of applied force up to 120,000 pounds of force. Other force calibrations also offered up to 2.25 million pounds of force known to within 0.01%. And that picture here is our primary deadweight calibration in our lab. Although we're talking about force today, we also have a torque lab. And our torque lab also offers highly accurate calibrations. So today we're going to be doing an introduction to force calibration for beginners. And I'm going to hand it off to Henry Zumbrun, the president of our company, who will be presenting today. Henry has been president of Morehouse since 2013 and has worked at Morehouse for more than 20 years. Henry has a passion for measurement accuracy and reducing risk associated with measurements that impact safety in our daily lives. One thing I've learned from Henry is that the far-reaching impact of force measurements on things like the planes we fly in, the bridges we ride on, and the cars we drive in. So now I'm going to pass it over to Henry.
Thank you, Heather. Yes, welcome to session one of a two-part session, Introduction to Force Calibration for Beginners. As Heather put, I do have a strong passion to help labs make better measurements, because when we make better measurements, we make the world a safer place. I've been in Morehouse specifically since 1994. I grew up in this company, with this company. When I started, I was mowing grass and polishing proving rings later, and then after college came in full time. I've been president since 2015, and my contact information is here. So as Heather said, this force measurements are very, very important. In fact, when Heather was talking about bridges, airplanes, and everything, we exist. This company actually exists because of boilers exploding. In the late 19th and early 20th century, boilers and steam engines were exploding. And by the 1920s, the problem was getting worse as the demand for these products was increasing. When a boiler blew up, the material was thrown all over like a huge bomb, and it often resulted in casualty. Ship plates were also a major concern. The plates were riveted together, and different materials could expand and contract at different rates, which could pop the rivets. It's speculated that fire on board the Titanic 5 days before the iceberg was hit contributed to weakening the ship and its eventual sinking. NIST has some really good articles on this. The reason all of this was happening is the material was not controlled and the testing methods were not good enough. Credit for this picture to Bradley Bilston, and it was around 1903. So we're talking about hardness testers. Here's a picture to the right of a 1921 Burnell hardness machine. What was basically happening here is the pneumatics in this device were inaccurate at best. You get kind of a reading, but the material lots were varying all over the place. And why this is important is because it's the hardness of the material that drives everything that is built. In order to determine the strength of the material, they need to develop a test protocol to prove the material was strong enough to withstand the forces exerted upon it. They used what was called a Burnell tester. The Burnell tester used a 10-millimeter ball, procedure shown there on the left, and a hydraulic cylinder to push that ball against the material. The indentation of the 10-millimeter ball was measured to determine the hardness. The main problem was the hydraulic cylinder used to generate forces was inaccurate at best. And so what did that do? And, that drove Morehouse to work with the National Bureau of Standards and create the greatest force measuring instrument devised by humans in 1925. Some may be shaking their heads, but in 1925, this proving ring was awesome. It solved a purpose. Engineering team, scientists go out there and scientists say, hey, we have a problem. Engineers work together to solve that problem. So my great-grandfather was one of those that was instrumental in creating the Morehouse proving ring to calibrate these Brinell hardness testers, which helped standardize the applied and force and provide a method to more accurately measure the strength of material. Therefore, this was created. The proving ring was created, started around 1925, hence our logo, the force and calibration since 1925. This was one of the earlier proving ring, serial number 14, calibrated by the Bureau of Standards, test number 47197. This was May 24th, 1926. That we're almost approaching 100 years on this actual calibration. Interesting document here is we're showing the Bureau of Standards certificate, the one back from 1926. Yes, we have records. Part of being 100 years old is cool because we have all these records and all these filing cabinets that have survived through the years, and we've digitized a lot of them, so we have our backups as well. Pictured left, cert from 1926. Pictured right, last calibration we have on record, 1984. The ring was in service for 58 years. That is something that often does not happen with load cells. However, I would say load cells are much later to carry. And if you choose the right system, load cells can be more ergonomic friendly, which means easier to use, easier for the technicians. We do offer digital proving rings for those that have analog. Question often gets asked, load cell versus proving ring, at which point I would say the digital proving ring would eliminate operator error, which may be a good upgrade option, or a load cell may be a good upgrade option. It's about having the conversation to determine what best fits your needs. As a participant, the groundwork for this, or what we would like to see happen, is that from attending this hour-long session, you will be able to have knowledgeable discussions regarding force calibration basics. So here's a question. I don't know if the polling's showing up, Heather. You can tell me if not.
Thank you. So,
what's that?
Yep. So I'm going to go ahead and do the question now for the polling. The polling function isn't working right now, but we are still able to ask the question, and we're going to get answers through the chat. So what I'd like you to do is in the chat box, enter A, B, C, or D. So we want you to rank your level of force calibration knowledge as beginner for A, enter a B if it's intermediate, C for advanced, and D for expert. And we're asking this question in the beginning just to kind of give us an idea of where people are coming from. This is a class for beginners, but maybe you're advanced or expert and you just want to go back and get a refresher. But this will help Henry get some background information into where you're all coming from and what your background is in force calibration. So go ahead and enter that into the chat.
See a lot of A's, a lot of B's, one C, which is good. I mean, if you're an expert and you just want to brush up on knowledge, that's, like I said, there's just general where people are, different levels and where this, may go. So appreciate everyone answering there. Like I said, we have a lot of B's, a lot of A's, some C's. Probably there might be, Heather, there might be one or two D's out there, but they probably are being refined to say advanced and instead, but that's fine. So if I were given this question, I would still go back and forth between D and C, just because I do a lot of reading and there's a lot more to learn. I know we don't know anything, everything about it. And if we started talking force calibration, such a broad topic, if we started saying, hey, high capacity force calibration, low capacity, there's even the capacity where we're talking about weighing in, a billionth of a gram's force, and these really, really small force applications. So anyway, but thank you, everybody. So a lot of different answers there, but primarily I would say on average we're leaning towards the B. So question, This is something people may have not put together. You come to work each day, you do force calibration, you're working at a job, you're new to it. Why is it important? Like, you know, did your company ever state why your measurements you make are important? Well, force is basically, everybody knows the story of Sir Isaac Newton. You know, an apple fell and he discovers gravity. But in his second law, he stated that force controls motion. Therefore, if we are to control the motion, we must control the force. Why is that important? Well, we'll get to that. We're looking at what force is. In general, force is derived unit. It's the SI base units for force. The SI base units are mass, time, and length. And this is taken from NIST. So all the different, you know, SI base units, we have the kilogram, meter, second, mole, ampere, Kelvin, candela. And to generate these other units, we work in combination with all these SI units. So for force, if you look at it, it shows over here the Newton, and how is that derived? And, you know, kilograms per meter divided by second squared. So that gives you your 3 units. If you're going to go for torque, the other thing that we do here at Morehouse, we do a lot of force and we do torque, and the same SI base units for both of them. The difference is torque is force times length. And here, anybody that's ever heard me speak is going to know this one. No one in the, here's a takeaway. No one in the world goes around saying meter Newton. You know, you buy a torque wrench, it says Newton meter, and then it says, most of them say foot pound. Well, foot pound is not torque, that is energy. So my pet peeve here is it is force times length. So we should always see Newton, the force first, meter, the length second, and we should see it as pound feet, right? Force times length, pound feet. So I don't know why manufacturers did that, but like, as I said, next time you look at a torque wrench, you can start wondering why it doesn't say meter Newton if they want to invert them. So force is mass times acceleration. There's a, you know, being a child of the 70s and loving Star Wars, we can't help but say, may the mass times acceleration be with you. The formal definition by the CIPM, BIPM defines 1 Newton as the force required to accelerate 1 kilogram to 1 meter per second in a vacuum. Hence that second squared that we saw earlier. Question 2. Again, we're going to use the chat window here again. What best describes calibration? Something someone needs to make sure equipment works the way it should, adjusting an instrument, and comparing a device that may be known against a device with a known to with a certain error. So if people want to start saying D is not an option, love it though. So we got a lot of C's here. I think the person with D. So anybody? So lots of C's. So yes. If we go to the definition of the VIM, VIM basically says a non-negative parameter. We're going to talk about this, but to just simplify what describes, and that was measurement uncertainty, just simplify what describes calibration. It is comparing a device that may not be known against a device known to within a certain error. So thank you for that. And if we're going to define it per the VIM, as I was getting into, and I wanted to define measurement uncertainty instead of calibration. That's because that's what I speak in lots of times. But per VIM, that is the International Vocabulary of Measurement. This is kind of where we get all our definitions, and definitions are very important in this industry, so we all can agree on the same speak and talk the same language. For those that are new to this, there's one of my people I have a pleasure to know. The person's name is Scott Mims. He wrote a paper which is free to download. You can go to it. It's called The Importance of Definitions. I highly recommend anyone read that paper because it discusses something I'm very passionate about, measurement risk, and the importance of getting those definitions right. Because if we don't get them right, if we're all operating on different definitions, different assumptions, then things like a 777 wing burning up happens. And those that are following in the news, what's current is that is an example of failure, almost catastrophic failure, where the titanium alloys that are used in the fan blades are breaking and snapping. And when they snap, bad things are happening, such as the engine and the sheathing, which is designed to kind of capture itself, is not working and falling to the ground. So really important that when we're looking at engineers and everybody else, that we're all speaking the same language. When we say something, calibration is part of that language. And the VIM is basically our reference to go back and say, what does this mean? There are other documents for other definitions, however. Calibration defined per the VIM, operation that, under specified conditions, in a first step establishes a relation between the quantity values with measurement uncertainties provided by measurement standards and corresponding indications with associated measurement uncertainties. And in a second step, uses this information to establish a relation for obtaining a measurement result from indication. Now, the importance here is note one, right? A calibration may be expressed by a statement, calibration function, diagram, curve, or calibration. In some cases, it may consist of an additive or multiplicative correction of indication with associating measurement uncertainty. Calibration should not be confused with adjusting of a measuring system, often mistakenly called self-calibration, nor with verification of calibration. Interesting topics for sure here, right? We have calibration and verification, two mainly different things. But the importance here is to say, in general, if you send an instrument to NIST, they are not going to adjust it. And for those that are beginners that may not know, NIST is our NMI, our National Metrology Institute, and that is the National Institute of Standards and Technologies. Usually they have the best uncertainties of anyone in the country for most disciplines and most parameters. However, they do not do torque and they do not do some other things, so that's where I say usually. But in general, if NIST does it, they're doing it at such a high level that no one else is doing except for other NMIs. So the other thing is, as I was saying, NIST is not going, more than likely, they're not going to adjust your instrument. And a lot of people confuse this definition of calibration with adjustment. They think, hey, I'm going to send that to somebody, we're going to adjust it. No, the adjustment happens, the calibration happens. You can use that data, a curve, to correct things, right? But where adjustment really happens is the second part of this lecture, is when we start talking about measurement risk, right? And decision rules. You send your theory may be, hey, I'm going to send it to the lab, and as a lab, we're going to say, we're going to go back and forth, what is the tolerance? And then we're going to agree on decision rules. And at that point, if the instrument fails based on decision rule criteria, at that point, that would trigger adjustment, which is not calibration. So very distinct. There's, if you want to do some more research on this and search, there's some good papers out there. Paul Reese wrote one, and there's also, you can look up Deming in the funnel experiment, as when you keep adjusting a process, there's some danger to it. And that's all I really want to say for this beginner course, is when you keep adjusting something, you say, I can tweak it, I can get it better and better. And all of a sudden, those little tiny adjustments where you think are getting good and pinpointing things make a process that's otherwise in control out of control. So, verification. That is a provision of objective evidence that a given item fulfills specified requirements. Example, a force gauge submitted to Morehouse is found to be within plus or minus 2 pounds as per the manufacturer's specification. That is, if you sent something to us and we didn't record forces applied and everything else, we could just send a certificate back that said, hey, we put some numbers, we applied some forces, and as such, we found that every point was within plus or minus 2 pounds. I caution people not to do that, though, because that's not having the discussion on decision rules that needs to happen with a conformity assessment. So verification should not be confused with calibration. Not every verification is a validation. An example is in chemistry, where verification of the identity of the entity involved or the activity requires a description of structure of properties of that entity or activity. So basics. There's two things really wanted to hammer down on calibration versus verification, how they're confused, how they're intertwined. There was a rumor that the VIM was going to be updated. I have seen that updated draft, and I have seen no changes to calibration or verification in that updated draft. So those definitions should stay the same with the new update. Basics. Alignment. Force calibration is very mechanical in nature. To have successful calibration requires the appropriate adapters. Different adapters can change the alignment and the amount of strain of the load cell. And then proper calibration requires the right instruments be chosen, which include force machines that are plumb, level, square, rigid, and have low torsion. Very, very important when you're evaluating a machine because force is very mechanical in nature. And the takeaway from this slide for the beginners is adapters, which we will talk about a little bit, and alignment, right? So I need to align something in my machine, and my machine needs to be plumb, level, square, rigid, and have low torsion, because if it doesn't, I'm going to get additional errors. Here's some basics. We often talk, this is really the beginner level, but we also talk attention calibration. How do you explain that? You know, when you say, hey, I'm gonna pull something into, all that means is we can be thought of, the tension calibration can be thought of pulling or stretching the material. So simple, these are all tension setups in various machines from Morehouse. Some of them can be tension or compression here. It just that one at the, just the one at the center bottom can be thought of as tension or compression. That one's not exactly clear, but the other ones are very clear. You're not, if you push on these with a clevis, you're not gonna generate force. So there's a deadweight machine on the far right. The load cell is oriented towards the force. Another more advanced takeaway, but if you're a Caltech, you always want to orient the live end of your devices towards the force. Then we think of compression. And this is interesting as far as our machines go, right? We have a force calibration machine here, the one to the left. This is our 2.25 million pound setup. And what's happening is that big bottom platen, if you see it right, it's the one left to the big green arrow, the bluish color, that is always moving upward. So whether if we're in compression or tension, it is always, our standard is always in compression. What this does, this design, it saves on calibration cost, right? Because you only have to have your standard calibrated in one mode. And we find that it's very effective to do this with changing setups and everything else and loading conditions, and usually best replicates use in the field, as people tend to make different setups for compression and tension, depending what they're doing. So that being said, and then the machine on the right, the force is coming down. So there's a yoke, and you see there's a stage beam underneath the load cell. We can fixture that load cell in compression or tension. The last drawing showed a tension fixturing. This one is compression fixturing there. So we thought of as compressing or pushing on the device. For most of industry is calibrating in compression. Depending on what industry, you have the weighing industry, they're obviously in tension, but for the general force and transfer to do testing machines and whatnot, most of that work is being done in compression. And we showed these pictures of the load cells, crane scales, and everything else. And the pseudo-technical term is a transducer. What we're looking at here when we're measuring force, there's three examples here, is we're looking at transducer. What is that? It's, in the broad sense, it's something that converts one type of energy to another. So a battery converts chemical energy into electrical energy. A thermometer, transducer that converts heat energy into mechanical displacement of liquid in a column. And then force or torque, quote, load cell, a transducer that translates the input of mechanical energy into equivalent electrical signals for measuring and or controlling the input phenomenal. Now that proving ring, you know, it had a dial, it was an analog instrument, you applied the force, you read the dial, the material compresses or pulls, and you read the dial. They're all, in the broad sense, these are all transducers, and as I said, it converts one type of energy into another. General with load cells, which is why people are here, because it's force, is a force sensor that receives a voltage or an excitation from a regulated power source, usually a digital indicator or signal conditioner, and sends back a low voltage signal when force is applied. That's what we're showing here is a strain gauge. When we actually apply that force, what happens? What happens here? The load signal is converted to a visual or numeric value by a digital indicator. You know, so we have no load on the load cell. When we have nothing on the load cell, the two signal lines are equal. And when we start applying a force, compression or tension, the voltage on the signal line increases very slightly and the voltage on the other signal line decreases very slightly. And what we're doing is we're observing the difference between them. Often you would see this, some people set these meters up to read in customary units or whatever unit they want to read in. Pounds force is a customary unit. Or they read, more commonly we see these, the raw data is millivolts per volt. So that's a ratiometric measurement where we're taking a millivolt reading off the load cell and dividing it by the voltage. So when you see that term millivolt per volt, that's what's happening. You're reading the millivolt signal, and then whatever the voltage is applied, 5 volts, 10 volts, you're dividing by that voltage. And when we make load cells, we often use multiple strain gauges, and we put those in different orientations. Here's one of the first 1 million-pound load cells that we made. It had like a Viscount 44 material, had 16 strain gauges. We used a lot of strain gauges because we thought the more the better. The more strain gauges you use, the better the averaging. The better the averaging, the better the repeatability and reproducibility conditions. Now, there is a point of no return. Typically, our design engineer is probably going to say, more than likely, is going to say it's going to be dependent on the application. What we do find, however, that this type of column load cell or some other, single column load cell is that 8 gauges are typically much better than 4 gauges. And then you kind of go past the point of diminishing return. All kinds of different load cell types. As I said, our engineer, it would depend, the gauging all depends on the type and what needs to be achieved, right? Single point way beam is going to be different than a bending beam, which is going to be different than a canister and then an S-beam. Now, those that have seen presentations before know that the S-beams are very susceptible to misalignment, as are your donut cells and some other. Canister cells, less susceptible. Those videos are online and on YouTube if anybody wants to go look at, the difference. We do a whole course on load cells. But shear beams, these are the ones that you saw in the picture. This shear beam at the top is shown without a base. We certainly recommend a base and integral threaded adapter because that improves performance. Clevis pin, and just all different types of different columns, and there's different applications for load cells. Some are tricky to calibrate, some are very easy to calibrate, some are, remember earlier said about alignment, some are to the point that if you do not align them, you will have huge errors. And then some have additional things like threading adapters. And we'll talk about a few common errors. As I said, there's beginners. What to watch for, we can call this. Is the force device loaded through the top shoulder or thread loaded? If thread loaded, how much engagement? So here we have a load cell. No problem with the load cell whatsoever. This is just a question to ask your customers. If your customers choose to send you instrumentation without adapters, what we're saying here is that the thread engagement of the adapter makes a huge difference. The picture on the left is a load cell. The picture on the right are 2 different adapters. Customer did not send us the adapters. So they basically said, hey, use your adapters and just tell us what you did. In this scenario, 2 very different adapters produced very large errors. So output was 10,001.5 with the adapter to the left with an 1.5 inch engagement, the longer adapter, and the output was 9942.3 with a 1/2 inch adapter with only a 1/2 inch engagement. There was a difference of 59.2 pounds on a 10,000-pound load cell. This is the problem. The customer said, use your adapter and tell us what you did. Now, we did that, and we said we loaded with an 1.5 inch of engagement. What happens if that customer is in a bind, right? Do they know if they only have a 1/2 inch engagement? Do they know that their error is going to be 59.2 pounds? That's a question. I don't know if they know or not. We obviously, as a calibration house, we want our customers to send the adapters in with the load cell. And it's important to note here, though we're mentioning adapters in compression are generally, load cells are more subject to errors in compression than in tension. Engagement errors like this are both compression and tension. But I'm going to show some additional examples where, compression's definitely something you need to have more concern with. However, on engaging the mechanical, the threads in the cell, we're going to get a different strain, which is going to give us a different output. The error on this device was over 0.5% on a device the customer expected to be better than 0.25, 20 times what was expected. Very, very important to ask the questions on adapters. Now, you may be sitting there wondering, like, are all cells this way? And in general, you need to test them. Most of them have their little quirks. Speaking of quirks, here's one where the force device is loaded through the bottom threads. There's a picture on the left, which is how we typically load it, and a picture on the right, if you know how most of our competitors load things, if they're using a standard machine that can switch from compression to tension, if they load it this way, it saves them time. And, they do, 4 calibrations to every, 1 calibration we can do by doing that. However, it's fine. Both of these conditions are okay. It's just you need to know how the calibration laboratory loaded your load cell. We find from polling our customers that many use them as shown on the picture on the left. And the difference, if you're looking at this difference here, it's about a 0.012% difference. Not a super lot when you're looking at force, but if that's your reference standard and you want to claim something on your CMC, if you're accredited, if you want to claim, hey, my measurements are 0.02, my measurements are 0.01 or 0.03, whatever you want to claim, that 0.01 can be very, very significant at that time, depending on what uncertainty you're claiming. If you're claiming 1%, a 0.01% error is not going to be that significant. If you're claiming 0.02%, you've already eaten half of your budget from just this one error, and that's why that's in there. The main thing, remember I said compression? This is one of the highest, this is one of the things we see a lot of, and there's a huge error. So customer sends us devices, and they expect better than 0.25, some expect better than 0.2, some expect better than 0.1, and then they don't send the adapters with it. We saw previously, the thread engagement was an issue with a 1.5 inch to 1/2 inch. However, this one's a bit more tricky because it's the hardness of the adapter. And if you think about it, we were talking about strain, the harder something is, the more strain, the more deformation it's going to put on the object, right? The softer it is, the less. So really, really important. We started the discussion about why we're in business virtually because the boiler's blowing up because of the hardness of adapters. And here it's made its way back into things with almost all load cells. And that top block that you used for calibration, that the customer absolutely should send you their top block, or they should have a top block for their load cells. And this is why. Just this 4340 versus a hardened top block, different Rockwell here, different setups. The two setups are noted on the right, and there was an error anywhere from 0.307 to 0.263% difference from the different hardness of top adapters. If the customer does not send us the top adapter and we use our adapter, they are at risk to being out by 0.3, 0.5, all kinds of percentage error that they may not be able to detect. So very, very important. And then I said this load cell, that was a multi-column type load cell. That was actually a single column type load cell there. We find the same thing with multi-columns. Typically, shear web load cells, this is new for this presentation. Everybody always asks, what about all the load cells? There is a difference, but if we start looking at error, look at that error. The difference is 0.001%. This is something that is probably much more forgiving for many systems, though there is, make no mistake, there is an error. And we generally find these errors to be low, 0.005%. Maybe if you're claiming 0.2% and your error is in the 0.002, 10 times that, probably much more forgiving, and it's not going to show up on ILC's interlaboratory comparisons, proficiency test, which is when somebody sends you a device and you have to report what that device is reading. So why is this all important? Why are we showing this? Because it's back to safety. What happens? What happens if you get the incorrect concrete strength measurement? What happens if you get the incorrect steel strength measurement? What happens if cables are not checked properly for post-stress, pre-stress, or post-tension. Things like this, picture to the right, a collapsed bridge happens, right? And if we look at it, here's what's going on. Engineers have to make all these calculations for bridges. Here's where I'm going to recommend some reading for people because I just love this book. It's a book by Henry Petrosky. It's called To Engineer as Human. And they talk a lot about bridge failures because there's so much going on in bridges. And so many people wanted to one-up one others. How long can we expand? How long can we make our bridge? How can we do this, do that? And you see some of them were put into place and collapsed. Today, this should not be happening. It still does happen. The bridge in Minnesota collapsed, some other ones. We should be able to get these measurements correct. We should be able to know the effect of environmental, which is wear on the bridge, rusting, everything else. We should be able to get all these things correct so these bridges do not collapse. So you can see some different things, tendon stress, pre-stress, what we're talking about, the reason that diagram just to show everything. So there is the one in Minnesota that collapsed, rush hour. Lots of people died. The NTSB, I think, did a thorough investigation. They found that the gusset plates were smaller than they should have been. My question to people is, was that gusset plate ever tested? I don't know. So the official thing on this bridge is, again, two-thing gusset plate ripped along a line of rivets, and additional weight on the bridge at the time contributed to catastrophic failure. Here's another one. This one, NTB. This is a bridge that was in Florida. NTSB said the errors were made in the design of the northmost nodal region of the span where 2 truss members were connected to the bridge deck, and that those errors resulted in an overestimation of the capacity and an underestimation of the load placed on that section. The bridge collapsed in Miami and it killed 6 people. In reading Petrosky's book, he makes mention to all it takes is someone entering a plus instead of a minus in a formula in software that does these analysis. And it's another example of why software should not be a substitute for actual testing. You go to work every day. Maybe the load cells, the transducers, the other equipment you see are used for some of these tests. What happens, right, if you don't get the hardness of that adapter right? What happens if that has an additional 0.3% error? They go to do a test, one of the stress tests. Again, they're thinking they're within 0.25. They're measuring they're doing their uncertainty. They're propagating it. They might be calculating the risk. They're assuming really, really low numbers when actuality, they're out by 10 times what they're putting out something that's 10 times higher or more than what they think. So really important on the lab level. This is called global consumers risk, and it's very important on the lab level, your lab level, to evaluate your calibration suppliers, make sure you're getting what you need, make sure they're calculating uncertainties correctly, making sure they're doing the appropriate risk analysis, using the right adapters, which isn't covered in any standard. You're only getting that from this course because I go out and try to teach that, because that is our highest error source that I see in this. So if things aren't getting done correctly at the calibration lab, you get the equipment, there's no chance that you're going to do it. Every decision, every measurement after that one measurement is made, or you have these error sources, is subject. And by the time we get to actual measuring the pre-stress and post-tension, you could be way out of line. People could make these measurements, think everything is okay, and then people die. So really, really important, and just in general, it's performed so frequently. We're looking at force calibration. You may go to work each day and say, what is this being used for? It's being used for a lot of different things. Almost every material item is tested using some form of traceable force measurement. Manufacturers do some sample testing on the products they manufacture, from the wood that was used to build your house to the cardboard that holds the toilet paper. All of that is tested, and I have some examples. What do you think about the titanium fan blades switch current in the Boeing 777? Why are they fatiguing so early? Is this a material issue? Is it a testing issue? We don't know yet. Where are they getting the titanium material from? Do they have the certs? How are they tested? What about, some other things in that process? So as I said before, if you as a lab are are taking some of this stuff for granted, making bad measurements, this increases the risk to everybody along the chain, and then bad things happen. Some examples, right? Some harmless examples, which testing the ripeness of an apple. Why may we care about that? Well, if we're on the West Coast, right, and we have hard apples versus soft apples, distribution, right? So we want to send the soft apples local, and we don't want to send them on a truck that's going to take 5 days to get to the East Coast. So what's going to happen here? Most likely, if you get this measurement wrong, somebody's going to have a few bad apples. No pun intended, but it's certainly there. And then testing the strength of coffee packaging using a quick release. This is just more testing, just different things. This is consumer. What happens if you don't get this right? Well, more than likely, the end consumer is going to curse a little bit and pull out a pair of scissors. So is this going to be catastrophic failure? No, though it's going to be bad for your brand and your product for sure. Testing the strength of fishing line. That's important. Some of you, I'm sure some of you fish. Imagine you got that, you caught that great fish that you've always wanted to. You went out king salmon fishing in Alaska. You caught that great and your line broke. How upset are you going to be? Is it going to be a loss of life for you? Probably not, right? But you're going to be really disappointed. Testing the adhesive peeling forces on foil packaging. Another example. What's going to happen here? Maybe somebody's old and has arthritis. Maybe you're young and have arthritis. If you can't pull that off, you're not going to be able to use the product. So again, just more testing the crushing strength of pills and then determining the force to remove the lid from a plastic package. I chose these examples specifically because the safety risk of a lot of this isn't very high, but it just shows that how testing is used in your everyday life. Then we get into some things where it is high, like an aircraft weighing application. What happens if we get this wrong? Anybody ever fly on a plane where the center of gravity is off or the weight calculation's off? Well, those that remember, there was a famous singer, Aaliyah, her plane took off and crashed because they had too much weight in it, right? If you don't get that center of gravity correct, it is a nightmare for takeoff and for landing and to just fly the plane. So very, very important, very crucial measurements here. A lot of this in the commercial industry is so regulated, but in the private industry, as I said, with the Aaliyah's plane, there are people that do some things that lead to bad decisions, such as an overweight plane, center of gravity's off. Very, very difficult to fly a plane with the center of gravity being off. So another question, again, wish we had the poll because it'd be nice for everybody to see, but if you just want to type in A, B, C, or D, and I'll read it. In your opinion, what is the most important reason to perform a force calibration? Improve product quality, prevent catastrophic failures, meet auditor or regular requirements, get peace of mind. So all of them are quite good. Everybody, yeah, B. So on the safety, I mean, it could be all A through D, right? A and B, product quality. Yeah, so as people are answering this, it depends where you are, right? We all do not want catastrophic failures because then bad things happen. But if we get everything right, we can actually improve product quality and we can talk about more profit coming to the organization, right? If they know their process is under control and their press is generating X number, X force, and they're checking it, how many defects do you think come out because of something being pressed? Not many. So we can get that. And if we have less defects, then we have, then we all ultimately have an increase in profit. But meet auditor regulatory requirements, of course, there's so many examples where people, skirted this, shoved it under a rug, and then bad things happened. And then peace of mind. What happens the next time you drive over a bridge, you fly in an airplane? How are you going to feel if you know that the company doing the calibration used a different hardness of a top lock, right? Is that going to impact to the point where something's going to fail? Is the bridge, if you're sitting on a bridge in rush hour, how do you know that those gusset plates were tested properly, right? So if we get the peace of mind is really, really concerning piece as a person that knows, as people in this industry that know bad things can happen if we don't get it right. It'd be nice to know that, hey, we know NIST calibrated Morehouse's equipment, Morehouse calibrated mine, in every chain along that way, that we got everything right. So if that happens, our peace of mind should be a lot higher. But yeah, obviously we don't want people dying. So measurement traceability, speaking of that, it started talking about it, right? It started talking about it early. There's 7 essential essential elements. And it's first the reference to international system of units. The second is unbroken chain of comparisons, measurement uncertainty, competence, documentation, calibration intervals, and measurement insurance. All these, right, are in NIST SP 811 chain of comparisons where end at primary standards for realizing of SI units. So we talked about the base units earlier, and we say, you know, again, this is just a refresh. That's number 1. That's most important. But then number 2, metrological traceability. So what that's saying is what I've said all along when we're talking about global, you know, global consumer risk and how that relates. What that is saying is, hey, I need to demonstrate that each link in this chain, which is a property of measurement traceability, which is a property of a measurement result, whereby the result can be related to a reference through a documented, unbroken chain of calibrations, each contributing to the measurement uncertainty. Basically saying, I need to get this right. I need to say, hey, my lab is here, Morehouse did the cal here, NIST did the cal here, and as long as we've documented, if we get everything right, the problem with this is that the auditors are not asking for accreditation. Most of them are not asking about the subtle things I showed you and the not so subtle, such as the top blocks. They're not asking those. They're just saying, hey, here's how you calculate measurement uncertainty. What's your formula? So that really needs, understanding that competence and understanding the error sources really need to go back into that. But what we're saying is basically this, and I have another slide after that. We're basically saying we have an established calibration hierarchy, and it looks something like this, right? Where we have SI units defined probably at the BIPM, and then, you know, the kilogram just went, before it was an actual artifact where NIST had kilograms, they sent them to the BIPM, and they'd all be compared against each other, and then they knew it was losing some weight and other things. But here's how this works, right? Each level. So we start at the BIPM, back to SI usually, then NIST makes a measurement, calculates the uncertainty. They have to absorb that other lab's uncertainty. Their uncertainty can never be better than the lab before them. Then you have a reference laboratory. What's happening? Uncertainty is getting larger, working larger, larger. So this is what measurement traceability looks like, basically saying, hey, for every link in the chain, the uncertainty has to grow. For force specifically, we have something that looks like this, right? NIST does fantastic measurements, of course, very expensive. We just had our £1 million standard calibrated by NIST. The bill was $38,000. Very, very expensive to do the calibration. So then you have labs such as us that do it at a fraction of that cost, really nowhere near that cost. We used to say we're about a quarter of NIST cost. Now I think we're safe to say we're about, you know, a tenth of NIST cost for that high calibration, the £1 million one. But so NIST does the cal. They're operating at uncertainties anywhere from 4 to 5 parts per million. We cannot be better than them. They calibrate our dead weight standards, adjust for gravity, air buoyancy, material density, and we get those numbers. We do our additional things for accreditation. So you can see they're 4 to 5 parts, we're 8 parts. Then accredited calibration supplier O2, working standards 0.1, field measurement half. Just really important here to see, like, in no case is one lab higher than lower than the lab that did the calibration. And again, that's reinforcing that. So if we go through it, BIPM is the highest level where the 7 SI units are realized. From the BIPM, the International Prototype Kilogram, an artifact, and that's spelled correctly because we're dealing with Paris. We're dealing with some French, and anyway, an artifact made of platinum iridium is kept at the BIPM under the conditions specified by the first CGPM in 1889 when it sanctioned the prototype and declared. Interesting. And then in the United States, we have NIST, designated NMI, National Metrology Institute. Then we have primary reference labs using dead weights calibrated by NIST as the reference standard. Here, Morehouse uses them. Accredited suppliers use secondary standards. Those are those such that are calibrated by primary. And then working standards and certified reference used in commerce and industry, traceable to above. And then the end result, I started showing you fishing line and fishing line, adhesive, pills, apples. The end result is they're using this equipment to test the equipment that's making those tests, the rebar test, the concrete test, the things that matter, right? You pour your house, you build your house with, typically most people using cinder block, they could use poured, other things. Let's just say concrete and wood. It's really, really important to make sure those are tested and that lot is tested. And then when a big storm comes by, your house doesn't get blown up, right? Or the roof doesn't get pulled off, that you're doing the right things and there's right testing protocols. Back in ancient times, for those that don't know, a tidbit of history, back in ancient times, if something were to happen to your house, if the walls of your house were to collapse and kill somebody in it, then the person who built the house, the family could go kill them. It's another thing in Petrosky has a book on engineering failures and success from failure, and he talks about the ancient times where this was pretty customary, that if you built something, you were going to honor it and you were going to repair it if bad things happened, right? And if really bad things happened, like loss of life, that you were going to be killed. So a lot of motivation to build the proper house. Today we're much more civilized, of course, but manufacturers do take shortcuts, and when they do this, it directly impacts the consumer. And we're just hoping that testing and the proper testing can reaffirm all of us. If you would follow us, like us, we like likes. If you could like us on LinkedIn, follow us on LinkedIn, Facebook, Twitter, whatever your choice is. And then there's some YouTube. If you want to dive deeper, we have a lot of recordings available on measurement risk, on adapters, all types of different presentations.